All right, so today we will wrap up this, detour that we have taken in this second module, where we jumped out of the discussion on heart modeling into a more generic discussion on the transition systems and model checking and linear temporal logic. So I thought it would be a good idea to just give you a very brief overview of sort of where we are in this module. And so where we began was this idea of safety for medical cyber-physical systems. That was a while ago, but that's where we started, that how can we prevent some sort of an error that could, put a safety critical and a life critical device like a cardiac implantable pacemaker, generate some sort of a undesired output or a non-safe output. And so in doing so, we then digressed into understanding the heart itself, which is common to the theme of this entire course, where you cannot model if you don't understand the domain, right? So what we did differently in this module was, while we were understanding the heart, we were also understanding this machinery of what is called a timed automaton, and that's sort of what you have done in your worksheet 5. You've implemented this timed automaton in Simulink and Stateflow as a transition system which has clocks, resets, and actions. And so we have this virtual heart model, and so then we transitioned into not looking at timed automata, but a generic framework of transition systems as a mathematical concept. So we got familiar with terms like traces and paths and words, and how we can describe the transition system as this tuple of 6 different elements. And in the previous lecture, I introduced linear temporal logic as this formalism of how do you specify behavior, or what you want your model to satisfy. How do you define it formally using these elements of linear temporal logic, which is essentially Boolean logic plus 2 temporal elements of until and next. And then we also saw examples where you can actually compose high-level temporal language formalism like always and eventually out of the grammar of LTL. And then finally, towards the end of the lecture, we saw some examples of how everyday movie titles and everyday things can be transcribed as a logical specification where there is zero ambiguity. And so today we will put everything together into this idea of model checking that I have been emphasizing for quite some time. So today is our the end of that tunnel where everything will come together. And then the only thing remaining in this module after model checking is the actual tool, right? So every module you will learn a new tool. The tool that you will learn in this module is called UPAL. It's a model checking tool. It's free to download. And then finally, we will wrap up by going back to where we started. And how can we actually do model checking using UPAL for our heart and pacemaker model? Okay, so that's where we are. We are near the tail end, more than halfway through. But I think it just helps, to get a lay of the land a little bit. So to do so, next week we will definitely go over UPAL. So unlike Energy Plus, where you had a choice whether you want to download or not, this time this is a much more involved tool. And the expectation is that you will not become experts in UPAL after one lecture, but you need to know UPAL to do the last assignment of this module. So UPAL is free for academics. You have to just visit upal.org. The tool looks something like what is shown on the left-hand side. It's very similar to how Simulink, you can drag and drop, or not Simulink, like Stateflow, where you can drag and drop states and transitions, but it behaves in a much more complex manner than Stateflow, I would say. So I am using this version as of this morning, so it works on the latest OS. So I think you should not have any trouble downloading. I think when you do download it, it prompts you whether you want to install some specific Java or something. So just follow that prompt and everything should work. Also, the worksheet 6 is out today, and as always, you can grab a hard copy. This is not a programming worksheet. This is just a worksheet so that you can understand transition systems and LTL, because we've had lectures on both. This is a short worksheet, relatively speaking, and it should take you a week at most to turn it in. It only has a few questions, and all of them are, is this a valid LTL formula? Does this model satisfy this formula? There are some verbal examples of people trying to use elevators or printers, and you have to specify that in LTL. So it's very traditional, like pen and paper worksheet. Okay, so you can grab a hard copy at the end of the lecture. So this is where we kind of wrapped up our discussion so far. We now understand all the elements of what is shown here, right? So we have a model or a transition system which has states, actions, ABCs. It has atomic proposition P and Qs. They have transition relations, and then there's a labeling function which tells us which proposition is true in which state. Then we have some specifications or requirements which are expressed in plain English or any language for that matter. And then we translate that or transcribe this specification into a formal notation that we did these exercise of how each of this is represented in some linear temporal logic notation. So we have both the ingredients that we require for model checking, right? We have the transition system and the specification. So now we can really ask the question that, does my model satisfy some requirement? And really what we are asking is, what is my model? My model is just a transition system. So we are asking, does the transition system satisfy some LTL formula phi? This is what all of the story has led us to. We now understand what a transition system is. We understand how we can derive phi from some numerical or English specification. So we'll try to answer this question by the end of this lecture. Right? How can we ensure that a transition system satisfies phi? Even before we understand how, let me tell you what does it mean for a transition system to satisfy phi. It means that for all traces of my transition system, they must satisfy phi. I'm not talking about one trace or one example. All traces, in fact, all infinite traces, because trace itself is an infinite sequence of which propositions are true. So all traces must satisfy phi. Only then I can conclude exhaustively that my model satisfies phi. If not, I only need the one counterexample, and that's enough to show that my model does not satisfy phi. And we've done this manually so far in the simple examples. Today we will build the machinery or understand what does a model checker do to deal with large transition systems like the one that you have been trying in Simulink. Okay, so the notion of model checking is that it is automatic and exhaustive, exhaustive being the key word. Once the model checker says the model M or the transition system satisfies the requirement, that means, sorry, I forgot to switch off my phone. That means that for all traces of the transition system, phi is valid or it is satisfied. Okay? So it's a very strict requirement, right? So it's going to be interesting to see how we can make such remarkable claims. But like always, I will distill it down into simple components, and then we will put this back together. So how do we even begin comprehending this idea that we need to satisfy something for all possible traces? Because there's a notion of infinity there, right? In fact, what you have doing in your worksheet 5 or have done on your worksheet 5 is akin to testing. Right? You ran your stuff for 10 seconds, no longer than 10 seconds, and it seemed visually or with some strict scope sort of visualization, you were able to convince yourself that this satisfies a bradycardia or whatever was asked. But you didn't run it for 1,000,000 seconds. What if at some point in the future some variable or some event is reached where your solution is incorrect? In fact, you can run it for however long you want. You can never claim that your Simulink model is truly correct. Because what about that 1,000,001th simulation or something else? So how can you prove that this is correct? No matter what, my model is correct. And that's sort of what we want to rigorously and exhaustively answer for a transition system. So the very first thing to check is that this is a mathematical object of the form this transition system, which is this mathematical tuple. Whereas LTL has its own grammar of true and P and whatnot, whatever we saw in the previous lecture. And I have said this before once that it's a good idea. It's not rule of thumb, but it's a good idea that you would want to stick with the same mathematical object when you are trying to model a real system. So right now we have two distinct objects. We have a transition system and we have LTL. They are separate mathematical ways of thinking about the world. So one idea of model checking is can we bring everything into this world of transition systems that will become easy for us to reason about their infinite properties. Okay, so we have a system model, which is this automaton. We already know what this is. We have a LTL formula. And it was shown, I think, in the 1980s, that for every valid LTL formula, you can convert it into an automaton, a special automaton, which is called a Büchi automaton. So for every valid, that's why we emphasize why is this valid LTL or not valid LTL, because this statement only holds true if your LTL is valid. For every valid LTL formula, there exists a transition system called a Büchi automaton, and I will teach you how that exists and why it exists in the first place, such that if there is a trace which satisfies that LTL formula phi, then that trace is accepted by the Büchi automaton. So there's one keyword here that is not clear what that means. Okay, let me break this statement down. So every, and I should say valid, which I did not, every valid LTL formula has a Büchi automaton, and the word which is ambiguous itself in this definition is, what do I mean by it accepts, this automaton accepts traces. The idea is that if you have a LTL formula phi, you can convert this formula into an automaton, let's call Büchi phi. So this is a regular transition system with some specific properties that I will describe, such that if there is a trace, let's say a trace of P's and Q's, which has this symbol. So this trace satisfies the formula phi, so this trace will be accepted in B of phi. And so I will define what accepting means in just a second, but that's the idea. That's what we will build on. We want to bring everything into the transition system mathematical space. So before we get to this definition, let me maybe draw a Büchi automaton just like we drew a transition system. It's very similar. So I'll draw some states. Let's say state S0, S1, S2, and S3. And this is my initial state. So first of all, we need to define the notion of what is meant by accepting. So in Büchi automaton, there is a special state called an accepting state, which is denoted by a double concentric circle. And I'll tell you in just a second what that means. Let me just draw some sort of transitions. Really doesn't matter. I can include a self loop here and here. Let me just transition on the same thing. So here is an automaton. Therefore, this object, which I can call Büchi, is also a tuple. It has the same elements as a regular automaton. So the first is a set of states S. We know very simply what that is. All four are belonging to this set. Then it has the next element, which is initial state. The arrow tells us what that is. What is the next element? It's the alphabet or the action space of the automaton. So here's already something of interest. Typically, when I drew a transition system, I emphasize that we'll use ABCs to denote inputs or actions, and P's and Q's to denote propositions or traces. But already you can see one special attribute, that the action space of a Büchi automaton are the atomic propositions of some transition system. Right? So I'll explain that later, but right now we know that the action space is nothing but the set P. Okay, then what we have the transition relation delta, which is also self-explanatory. We can make a set of all possible transitions. And then what were the other two elements in a regular transition system? We had the atomic proposition, and then we had a labeling function. Here, we don't need any of those. What we have is a new set F, where F is the set of accepting states. How do I know that which are the accepting states? They are shown by this double concentric circle. So what are we trying to do? Given a LTL formula phi, I can generate B of phi such that any trace which is a set of P's and Q's, which satisfies phi, will be an accepted trace in my Büchi automaton. So what is an accepting trace is the next question. Everybody with me? Okay, very simple definition. A trace is accepted by the Büchi automaton if and only if it visits the accepting state or the set F infinitely often. That's the definition. So a trace can be accepting or non-accepting. By definition, it is accepting if it leads to this path in my Büchi automaton, where in this case S1 will appear infinitely often. If that is true for the trace, then yes, this is accepting trace. So let me orient you a little bit and then I'll pause for questions. Who is generating the trace? Let's begin there. We have a model M, which is a transition system. The transition system experiences some inputs, which are the ABCs of the world, and that leads to some path which produces a trace, correct? We are all good so far. This is what we've been doing for like a week or so. So transition system produces states. These states, or this trace is the input or the action space of my Büchi automaton. So it's almost like the Büchi automaton is consuming the trace from a real model or a transition system. So this trace will induce its own path in my B of I. And I want to look at the properties of this path. If this path contains the accepted state infinitely often, then this trace is called accepted. And if that is not the case, it is not accepted. Questions on what? Don't worry about why you need an accepting state. This is just definition, okay? So with examples, the intuition will be built. Is the definition clear of what is accepting and what is not accepting? Any questions on this? Okay, so this is exactly what this slide was meant to say. It's another tuple with all of the same things as before, except there's this new set function f, which is nothing but a set of accepting states. And we denote them by this double circle. So a sequence of states or a path in the Büchi automaton is accepted, and notice that it's if and only if. It goes both ways. If you can find an accepting path in the Büchi automaton, it will satisfy the LTL formula phi for which the automaton exists. It applies the other way too. But this is an accepting path if and only if it contains the state, the accepting state infinitely often. That's the definition of a Büchi automaton. So let's look at maybe an example, right, to build some intuition. So I think this is a straightforward example, which is just saying, here is a Büchi automaton. How do we know this is a Büchi automaton and not a transition system? Because it contains some weird state, which is not present in a transition system or a regular transition system. So let's answer all of these. What is S? It's very clear. It's S0, S1, S2. I is just S0. So this is just S0. The alphabet or the set of actions of this Büchi automaton is what? It's P and Q. For this Büchi automaton, P and Q behave like inputs. For a regular transition system, we have been using P and Q as the notation for the trace. And that's important to get used to that idea. Finally, we have delta, which is a set of transition relations. And what are the accepting states of this automaton? It's actually just S2, because that's the only one which is this double symbol. Okay? So this is just an example to get used to the idea. So let's look at the same example, and can someone give me a path? What is a path? Just recall, it's a sequence of states, infinite sequence of states. Can someone give me a path on this Büchi automaton which visits the accepting state infinitely often? What are some examples? Yeah. That's not a path. So P's are not paths. Give me a path which is a sequence of states of this Büchi automaton. And I assume you meant S2 forever, okay? That's a valid path. Any other path which could visit S2 infinitely often? Okay, very good. So we go from S0, S1 to S2, and what you are saying is this can repeat forever. So these are all paths that visit the accepting state, which is S2, infinitely often. Right? So the first one is this example, which is accepted by this Büchi automaton. The second one is switch between S1, S2, but S2 will be visited infinitely often, so it is also accepted. Why accepted? Because S2 is the accepted state, which is why it's highlighted in these paths. Let's look at a path which goes from S0 to S1. Then it does go to S2 here, comes back to S1, but never leaves S1. It just stays here forever. This is not an accepting path because it does not visit S2 infinitely often. It does visit once. You could even say it could visit a finite number of times, but eventually it will loop in S1, so you'll never see S2, so it's not an accepted path. Yes? So you are asking where is this accepted state coming from, and we'll get to that, because I haven't told you how you would design a Büchi automata. I have just said that a Büchi automaton is a representation of phi. I haven't shown you why that is true and where is this magical accepting state. So we'll get there just shortly. But this is just intuition to convince ourselves what is an accepting path and what is not. Okay, it's straightforward, but it helps to go through examples. You can even think of, well, what actions or what is a sequence of alphabets? It's called a word, right? Remember, that's the definition. So what word would induce this path, right? So we can say if you have to go from S0 to S1, you must have seen a P. Then from S1 to S2, you would have seen a Q, and then Q forever, right? This word, which is a sequence of alphabets, and remember, P's and Q's are the alphabet of this Büchi automaton. They may be traces from another model, but for this transition system, they are alphabets. So this is a valid alphabet or a word which can induce an accepted path in my Büchi automaton. What is the alphabet corresponding to, let's say, sigma 2? It's P. Then you must have seen a Q. Then you must have seen a P. Then you must have seen a Q, so on and so forth. And similarly, you can deduce what word would have induced this path, which is not accepted. Okay? So nothing special besides this requirement of visiting the special state infinitely often. That's the only thing which has changed. Yes?
Wouldn't it be similar with the first one if you write down the word for the third one?
So let's do that. So P, you need a Q to go to S2. Then from S2 to S1, you need to see a P. And then from S1 to S1, you need to always see a Q forever. So I meant this is P and Q are going to repeat, and here I think only Q repeats. So is it clear what's our accepted path? Good. So this is exactly what we discussed, right? So what will induce an accepted path is an accepted word. And the key thing is that these words, they look a lot like traces of a regular transition system. That's the connection, right? Earlier, for the last two lectures, I was saying PQs are the propositions and they are the output of a transition system. It's a trace. And now I have flipped on my own definition that for a Büchi automaton, what is its own action space or input space looks a lot like it's the output of a model or a transition system. And this is how we will connect the two. This is how we will connect the transition system to an LTL formula. Here's what we'll build on. Yeah. No, go ahead. All questions are welcome. So are you saying that you have P and then this? Yeah. So this can induce a path S0 and S1 forever, which does not visit S2 infinitely often. So this would not be accepted.
But we can show the one as the right one. Is that wrong?
Okay, so let me give you an answer. So the question is that you have an example of a word which can induce multiple paths. We've actually already seen this in a regular transition system, that can also be the case. So one thing that you have touched upon is that my transition system, if you haven't noticed already, is non-deterministic again. Okay? When I see a queue, two things can occur. So his question is PQ plus considered an accepted word? Because in one universe, you will never see S2, but in the other, you do, which is the example shown here. And so the answer is yes, because you need at least one path. You don't need all. You do need all traces from the model must satisfy a formula, but that's a different thing, right? What you are asking is PQ plus an accepted path? The answer is yes. Even though there is one counterexample where you don't see S2, you just need the one example where you do visit the accepted state infinitely often. That's a good observation. Okay, so we've already seen examples of what words are accepted by this automata. These are the PQ plus and other stuff. So here's another, and I promised the last definition. The set of words which are accepted by a Büchi automaton is called the language of the Büchi automaton. Okay, and intuitively, you know, a word is a sequence of alphabets, and a sequence of words or a set of words is a language. So that's just a definition that we will use later. So the notation L of B is that the language of this Büchi automaton is the set of words for which there exists an, right? This is exactly what he was asking. You just need at least one instance for that word to be accepted by the Büchi, and that's enough. It will belong to the language. So any more questions before we proceed further? So still definition, we are playing with mostly definitions. Let's actually start looking at how do we use it for model checking. We've already seen that it is just the case that Büchi automaton are non-deterministic. So I just wanted to emphasize that, and that's also shown here, right? This is a non-deterministic. We will actually exploit this property when we build our Büchi automaton, that non-determinism is allowed when you try to build this Büchi system. So what remains to be seen is, by some magic, which I haven't shown you, you can translate the LTL formula phi into B of phi, which is a tuple and its own transition system called Büchi. And now we want to see why is it, or how do you prove or show equivalency between LTL and this transition system. So really what we are going to discuss next is examples of LTL to Büchi. So let's look at this example that we've already sort of seen many times before. So for my sanity, can someone just yell out in plain English what this is trying to say? What is GFP? Always eventually P. Is there another way to say the same thing, which is not LTL, but just regular conversation? What is this really trying to tell you about P? There exists P, but can you say something more? What is the always telling you? Because there exists P can be just FP, right? So what is GFP telling you about? Can you say that again? When you encounter P, it will occur forever, which is exactly, you're all right, okay? Always eventually P is what this is saying. Can you rephrase it and tell me something about how many times will P occur? Infinitely. I can say or I assert that what this is saying is P will occur infinitely often. Process that and tell me if you don't agree. Always eventually P is the same thing as saying you will see infinite P's in your trace. Okay? So let's look at what is a Büchi automaton such that if some trace satisfies this LTL formula, it will be accepted by that Büchi automaton. So without showing you how, I'm first going to show you the result. Okay, I present to you this B of phi, where phi is GFP, and then I hypothesize that if there is a trace where P occurs infinitely often, it will be accepted by my Büchi automaton. So let's convince ourselves that is indeed the case. So let me pick some arbitrary traces, okay? My first trace is Q, 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 P plus. We can even be Q, P, Q, P, Q, Q, P, P, Q, P plus, okay? I can go crazy as many traces as I want. Let's see, does this trace satisfy phi? Always, eventually, P. Yes, it does, because, you know, P lasts forever after this point. So indeed, it says not always, eventually P, it just satisfies always P also. Does this trace satisfy always, eventually P? Yes, because we see the same thing. There's a bunch of different stuff, P and non-P, but always, eventually, you will see a P. Now let's see if these two traces are accepted by my Büchi automaton. So you begin in S0, and then you see a Q in the first one. So let's look at phi 1, trace 1 and trace 2. In trace 1, I first see a Q, and if I'm in S0, I will just take this transition, because I don't care if it's not a P. Okay? On true, I can just self-loop. I can do all these self-loops on these initial Qs or consume the non-Ps and then see P plus, and then I go to S1, and then I can loop in the accepted state for infinity, which is why it is an accepting trace. And let's do the other one where you see a Q, so you do the self-loop on S0, then you see a P, you may again take this transition to S1, then you see a Q again, so you can come back to S0, and this can happen many, many times. If you see a sequence of consecutive not P's, you have this route to consume them. But again, there will come a point in this trace 2 where once you transition to S1, you can remain in S1 forever. In fact, not even that, I can say QP plus is also a valid, it will also satisfy this formula. If you just keep alternating between QP, QP forever, you do see P infinitely many times. And why is it accepting? Because it will satisfy this loop. You can keep visiting S1 every alternate step.
Well, the first trace in my state asks you forever. Okay, that's certainly true. So even
Good. The question is that this seems to be too permissive. That even not just Qs are getting consumed, P's can also get consumed here. And that is true. But remember, this is a non-deterministic automaton. Why? Because when you are in S0 and you see a P, you can do two things. You can self-loop on S0 or take the transition to S1. And we only need one of them to be an accepting path for this trace to be accepting. Okay, so when you are in S0 and you get a P, the universe becomes parallel. In one universe, you remain in S0. In the other one, you transition to S1. And in fact, on every input from here on, if it is a P, you keep branching out into parallel universes. Because every time you are in S0 and you see a P, you can take true. But we only need one path to be accepting. So that's why each of these, they satisfy the formula always, eventually P, and all of them are accepted by this Büchi automaton, which is drawn here. Let's look at a counterexample. Let's look at an example which does not satisfy always, eventually P. So you can say P, 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 and then Q repeats forever. So you do see a lot of P's, but then you never see a P, which will violate always, eventually P. So is this accepting? Let's explore this. On each of these P's, you can do the non-deterministic transition. In one universe, you will go true, and the other you will go S1 and then loop on S1. But as soon as you see Q, you come back to S0 from the one thread where you went to S1, and then you never visit S1. And in the other universe, you never actually go out of S0. You just remain in S naught forever. So none of them actually visit the accepting state infinitely often. Therefore, this is not an accepted path, and it should not be because it does not satisfy the LTL formula. So remember, B of phi will accept any trace which satisfies phi by design, by construction. Likewise, if you can find an accepted trace in B of phi, it will satisfy phi. It's because it's if and only if. Okay, so again, I know this could be dense, so give me questions so that this is clear. Let's start by what should be clear. Does everyone agree that this Büchi automaton will only accept traces which satisfy always eventually P or infinite P's? Is that clear? And is the other direction clear? If you can find a set of accepted path inside the Büchi automaton, it will automatically satisfy infinitely many P's. Because to be an accepted path, you have to visit S1 infinitely often. The only way to visit S1 is through P. Those are the only entry points. So if it is an accepted path, you must see infinite P's to infinitely often visit S1. So that's why there's a if and only if relation. So questions? Yeah?
For this specific example, everything is perfect, but I don't know what will happen if we change everything or if we have more like.
Yeah, so again, the thing which I haven't shown you is how did I derive this Büchi automaton structure for this LTL formula? And so the question which is completely appropriate is, well, what if there was, some transition where it was not carefully chosen, where, it doesn't satisfy and still is accepting? So let's do that. Okay, now you will design a Büchi automaton such that it will satisfy some formula. So let's first orient ourselves again, right? So the bigger picture is we have a model M, which is just a transition system. This is our business as usual transition system. It has an action space or alphabet A. It has atomic propositions P and Q, right? So this is, let's say, our heart model, just for example. A sequence of these alphabets or a word induces a trace in my model M. And I want to explore the question that does M, and this is the symbol for satisfy, phi, where phi is always eventually P. This is what I want to explore. And what I have shown you is that you can construct a Büchi automaton B of phi for this LTL formula such that if the P's and the Q's, the traces of the system are accepted, if all the traces of the system are accepted by my B of phi, then M satisfies phi. Is that clear? For all traces of M, if they can be accepted by B of phi, then we are done. Because by definition, only thing which can be accepted is if you satisfy phi. So if you can show that all traces of M are accepted in my Büchi automaton, then you are done. Then the model checker can say, yes, M satisfies phi. Correct? But we know in this picture, visually, does this transition system satisfy the formula always eventually P? Can someone give me a counterexample in M that does not satisfy GFP? Give me a trace which is possible in M where P doesn't occur infinitely often. So let's look at M, right? M is this object right here. What is a trace in this automaton? Is there a trace somewhere here where P doesn't occur infinitely often? That's not a trace. A is a word. Okay, so I know what you mean always, but I will correct you because that is what we emphasize, correctness. So P forever. That's what you mean, right? Or Q forever, sorry. So here is an example of an output where you may see all A's, which will induce a trace Q forever, which clearly does not satisfy always eventually P. You never see actually any P. So if it does not, then this should not be accepting in our Büchi automaton as well. And let's convince ourselves, if you always see Q's, you can do nothing but remain in S0. You can never go out of S0. Because the only way to go out of S0 is to see a P. Therefore, indeed, you have found a counterexample, and we have verified that it is not accepting in my Büchi automaton. Is it clear? This is what a model checker is trying to do. It's trying to consume the trace from a transition system and feed it into the Büchi automaton for the property that you have specified, which in this example is always eventually P. But it could be any valid LTL formula, and it will do the same thing. It will consume these traces, and if they are all accepted, you are done. If it finds a single counterexample from M which is not accepted, you have found a counterexample. And you have shown that M does not satisfy phi. So let that settle in for some time. Okay, so we found a counterexample. There are other examples too, where you visit P, or where P does occur, but not infinitely often, but it's still a counterexample. Okay, so let me draw this so that everybody is on board. We have a transition system M, which accepts the ABCs from the real world or the environment. It produces traces, let's say omegas, which are a sequence of atomic proposition P and Qs. There could be more than P and Q. I'm just using an example. Right? So this has nothing to do with Büchi automaton. This is a regular transition system. Then you come along and you say, I want to check, does this transition system M satisfy a LTL formula phi? So what we do is we say, let's first take phi and convert it into a Büchi automaton B phi, such that the inputs to my Büchi automaton are the traces of the model. And if all the traces of the model M satisfy or are accepted in B of phi, then I can conclude that the model M satisfies phi by definition of the Büchi automaton. And I only need to find at least one counterexample where it is not accepted in B naught phi, and I'm done. I have a counterexample that says M does not satisfy phi. Is the connection or this picture clear? So it's almost like saying that you have your model M and you have B of phi, and they are running sort of in parallel, where one is producing the trace that is getting consumed by the other. Is the concept or the intuition clear? Any questions on this? Because then I'm going to jump into some more examples. Okay, so wait, let me tell you one more thing before we jump into an example. So this makes sense, right? But let me ask you this. The most difficult part of this picture is this condition. For all traces of M, you have to see whether they can get consumed by B of phi or not. So if my transition system has a lot of states, it's going to take a while to explore all possible transitions, or all possible traces, sorry, not transitions. Everybody sees why this can be a problem, that you have to ensure every trace of my model has to be accepted by the Büchi automaton for the model to satisfy phi. So that seems like a very, very hard work, and it is. So we use a very brilliant trick to avoid any of that. Here's what we do. In the same picture, if I want to check, let me make some space here. So I want to check, does my model satisfy phi? This is my question. So what I do first is I take phi and I build B of phi. However, now I say, let me actually take the negation of phi, which is also valid LTL, and build B of not phi. So B of not phi is a Büchi automaton that will only accept a trace which violates phi, by definition of what a Büchi automaton is. Is that clear? I'm constructing another automaton, B of not phi, that will only accept something which violates phi. And then what I do is, I run my model and B of not phi in parallel. So rather than looking at infinite traces, if I even see one accepting trace in B not phi, I have shown a counterexample. And now the question is, how do you actually run them in parallel? That's the only last piece of why this would not work or why this would work. But do you understand why you have to build this complement automaton? To avoid the hassle of looking at all traces, I just need one counterexample. And you may still think that how are you finding this needle in the haystack? Because 1 out of infinity is still a big search. And I will show you that it can be done very, very fast. It's actually a very simple, straightforward algorithm. But is the intuition clear? How is a model checker working? I'll repeat it one more time. We want to answer the question automatically and exhaustively, does a model or a transition system satisfy the LTL formula phi? For this, we want to bring everything into the mathematical space of transition systems. So with some hand-wavy logic, which I haven't explained, you can build a Büchi automaton out of a LTL valid formula. So now you're only dealing with automatons. That's great. 2 thumbs up. Now, instead of looking at all the traces which are accepted by B of phi, I just want to search for one trace which is accepted by B of not phi. Because not phi, if there's an accepted trace, that automatically by definition will violate phi. And I would have found the counterexample and conclude, yes, it is the case that it doesn't satisfy phi. If I cannot find a counterexample, then M satisfies phi. Good? Yes.
So for the B of not phi,
Yeah.
will the accepting states just be like all the ones that weren't?
No, no. So you can think of this as not phi is its own LTL formula phi 2. And so there will be its own Büchi automaton phi 2. Okay? So let's actually get into the weeds for just that question before I show you how everything works. So this is just a recap of the intuition. B of phi will accept exactly those things that satisfy phi. So B of not phi will accept exactly those things that violate phi. So let's look at our same example. We were looking at phi where it was always eventually P. So what is not phi? And you can prove this. In fact, I think this is one of the homework problems, that the always and eventually are kind of duals of each other. So if you negate one, you will get the other. And if you break it down into the and the negation itself and the next state as well. So if we take the negation of phi, we get eventually always not P. Which, if you think back, all that is saying is, all this is saying is that P must occur finite times. That's all it is saying. Which makes sense again, because always eventually P is that P will occur infinitely. So what's the negation of P will occur infinitely? It's that P will occur finitely. Which is the same as saying that eventually there will be a case that you never see a P. So eventually always not P. Okay, we've just taken the negation of phi, and this is what not phi is. So here's the question for all the chips. What is the Büchi automaton of this expression? Eventually always not P. So I need some suggestions on what this could be. I'll even help you out by drawing an initial state and take it from there. What more states, transitions can we define? What is your goal? Your goal is to build a Büchi automaton such that it will only accept those traces that satisfy not phi, or satisfy eventually always not P. So let's look at some suggestions. Yeah. So we were saying self loop on Q. I'm going to interpret Q as not P. Okay, because it could be anything. It could be Q, M, R, S, T. But do you need anything else? there is no accepting state yet in this Büchi automaton. Right? For this to be a Büchi automaton, we at least need one accepting state. So, yeah. Oh, so your suggestion is just this. So what happens if you are in S0 and you receive a P in this example? So you are saying this. Okay, that's fine. That's fine. This is how we learn. So let me draw another one. So S0. Let me even say that I'm drawing an accepting state for you. I'll help you out. I'm your friend. I want you to like figure this out. So now tell me what transitions are possible so that an accepting path in the Büchi automaton will satisfy eventually always not P. So yeah, let's go. Yep. Yeah. Sorry, slow down. So I heard this, and then what do you do? Oh, so this. So okay, let me give you a counterexample already. So what if your trace is Q, P, Q plus? So you cannot handle this first Q. If you are in S0 and you receive a not P, what do you do in this picture? So can you solve it? Can you augment this? So you are saying this? Wait, so, well, if you're going both ways, you are just doing this. Okay? So that. So let me ask you this. If you are in S1 and you receive a P, what happens? So think about that. Let me draw a fresh one. I'll keep going until we figure this out. Other suggestions? Yeah. Yeah. So wait, so tell me all the ones. So what do I do with S0? So P on S1 and then what is the condition on the loop? Oh, true. Okay, interesting. And this. Okay, so let's look at a trace which is P, or forget P. Let's just look at the simple trace Q plus. So first tell me, does Q plus satisfy eventually not always not P? Does it satisfy our not phi? Yeah, it does, right? Because eventually we never see a P. In fact, we never see a P at all because the trace is not Q plus. So is Q plus accepting in your automaton? It's not, right? Because the only way you go to accepting state is when you see a P actually. So still not quite there, but interesting idea. Let's do one more before I reveal the answer. Think about what I'm asking for. I'm asking for a Büchi automaton that can accept this. So if we see a finite number of P's, it should be accepted by my automaton. If there are infinite P's, it should not be accepted. As simple as that. So let's try it one more time. More suggestions? Yes, Lauren?
Is there a reason that we can't take what the automaton that you showed us a couple slides ago, and then where it said P, now make it say not P, and where it said, actually, yeah, where it said Q, make it say P.
So can you tell me what that would look like?
Okay, so you're maybe a self loop on the initial state.
And what is the criteria for the self loop? Okay, and then why would you transition to S1 on?
So
Okay, and do you do anything extra in S1
At S1, there's also a sub
on?
Originally it was P, so now it's going to be not P.
Interesting. So her idea was to take the same automaton that I showed you as an example of always eventually P or infinitely P's, and kind of take the automaton equivalent negation of that, which I haven't shown you how, but I think sort of you're intuitively deriving this. So let's look at this one. This is an interesting idea. It says you can remain in S0 when you see true, and then you transition into S1, and then you remain in S1 if you never see a P again. So what do we want this to do? We want this to accept a trace with finite number of P's. So let me build a trace, right? So let me say Q, Q, Q. Okay, it always has to happen at least once in my it's Q, Q, Q. Then I can say P, 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 then Q plus. Does this trace satisfy this LTL formula? Eventually, always not P. It does, because eventually, always, it's not P. Is this trace accepted by this automaton? So you, yeah?
Are we missing one path? I have in my notes, I copied it down from a different slide, but I have in my notes a path connecting S1 to S0, so that if we're in S1 and we receive a P, we have someplace to go.
Okay, so you are suggesting this. Well, let's ignore this for a time being. Or let me give you the answer. The answer is this is enough. What she's already suggested is enough. So why is this an accepting path? Because, again, I know it helps if you think in terms of what the requirement is. It can be confusing if you think in always and eventually, because they are not that intuitive. The requirement is you have to accept a trace where P occurs finite times. By definition, there will be a point after which you never see a P. And we want that trace to be accepted by this automaton. So, no matter what these initial atomic propositions are, I can consume all the P's while being in true. And then when I reach that point after which I will never see a P, I go to S1, I will be accepting because I will remain in S1 infinitely often. So I don't need to actually go back to S0, because if there was a P in the future, I would have never made the transition in the first place. I would have remained in true until I reach the point where eventually always not P occurs, and that's my trigger to transition to the accepting state S1, because eventually always I will remain in S1, therefore it will be an accepting path for B of not phi. So an accepting path of B of not phi will be a path which violates phi, where P occurs only finite amount of times. And so I think this is exactly the solution here. So this automaton is enough to satisfy eventually always not phi. Questions on this? I still haven't shown you a methodology to go from LTL to Büchi, but with this example, it should be more at least clarifying what is the purpose of B of not phi and why, in this case, actually non-determinism is our friend, because non-determinism allows us to consume all the finite P's before we go to S1 and remain in S1 forever. So, is this clear? Or have I lost you? Are you still with me? Why this makes sense? Okay. We still have time. Let me just complete this chain of thought. So, okay, right? The idea is that if my transition system generates a trace which is accepted by B of not phi, this means that it violates phi and therefore it doesn't satisfy the LTL formula phi, which we've already sort of discussed when we are talking about the intuition. Right? So I only need one trace out of my model M to be accepted by B of not phi to show that my model doesn't satisfy this criteria. So how do we do that? How do we implement this? Let's say we have a model or a transition system, or we have a transition system. We have a property phi. We negate that property. We get not phi. Then I build a Büchi automaton, A or B of not phi. And I want to run my transition system in parallel with my Büchi automaton so that it can consume the traces of my transition system. And if I find even a single trace which is accepted by B not phi, I have shown that M does not satisfy phi. So the final piece is this running in parallel. So let me show you that. This is the same plot again. So skip. Yeah, so let's look at this picture. So I have a transition system M. I have just augmented our simple example so that in each state, all the inputs are valid. So there's no deadlocks. Okay, that's all what it is. So this is my model M, and this is B of not phi, where phi is the same thing, always, eventually, P. Okay, so not phi is the exact example that we saw. Now my question is, how can we run these two things in parallel so that we don't have to do this infinite search, even though we are searching for the counterexample in this case? So here's the idea. We take what is called the product automaton. This is the last thing I'm going to talk about today. This was already actually brought up when we were studying Simulink. Someone asked, why can't we just have one automaton for the node path and the node as one big humongous automaton? So we could have had that, and that would have been the product automaton of the three automatons altogether. So what is this product? Let me show you an example. So we have a transition system M, which is this simple example, and we have the Büchi automaton of not phi. So in my product, I will take the product of every state with the state of the other transition system. So in my product, I will have a state called Q S naught, and then I will have a state called Q S1. I will have a state called, let's say, P S naught and P S1, which is the product of this state with the two Büchi states. And then I will have a state called PQ S naught and PQ S1. And since S1 is an accepting state, in my product, I will also denote them as accepting states. So simply put, the product of an automaton with 3 states multiplied by a product of a multiplied by automaton with 2 states is 6 states, each with each. Let's look at some transitions. So I say that if you were in Q in your original model and you saw A, you can remain in Q. Correct? This loop right here. This is just one of the transition relations of my original model. When this happens, what is the proposition I'm outputting? It's Q. So let's say I was in S naught. So I can say this is the initial state as well, based on the product. If I'm in S naught and I see this Q, what can I do? I can remain in S naught according to, I can go to S1 because this is not P. I can take this transition on a Q. I can do this as well, but let's say I take the other one. So what is happening is in my product, I'm going from QS naught to QS1 when I see an A in the original model. So I can say that. Let me pause again so you understand what has happened. Everybody understands how the product states are. They are just one-to-one element-wise product. Let's just call it that. And now I'm looking at the transition relations in my original automaton. They can cause some transition. When they cause a transition, they produce a trace in my original model. I look at that trace and see how will that change my state in my Büchi automaton. And that will lead me to one transition in my product. Let me draw another one, and I'll explain it in just a bit. I will say that this is also true. So if you were in Q and you receive a A, B, or C, which is right here, you go to a P. So your output of the model is P. And so if you were in S0 and you receive a P, you remain in S0 because of this true self loop. So effectively, we have transitioned from QS0 to PS0 on ABC, which is exactly what this is in the product. Right? So you can convince yourself, but let me draw it, that you can make the complete picture. So let me draw all transitions. And then there is this transition as well. So I present to you that this product automaton is exactly equivalent to both of these automatons running in parallel. Where we've seen two examples, but in interest of time, I've just shown you the others. You can build them yourself. It's not that hard. So why did we build this product automaton? So here's the aha moment, which might be too late for that in the lecture, but it is anyways. All I need to check is, in my product automaton, is there a cycle which visits any of the accepting states? Otherwise, is there any loop in my product automaton which visits an accepting state? If there is, then there must be a path in the original transition system which will visit the accepting state infinitely often. And if there are no loops, then there is no path that visits the accepting state of B of not phi. Therefore, if there is no loop in this product automaton, M satisfies phi. You cannot find a counterexample if there is no loop. So we've solved our problem of searching over infinity. Because this is a finite automaton, and we only need to discover if there is any loop or cycle in this graph. Forget about even automatons. This is a graph problem now. Given a graph, can you figure out whether there is a cycle which contains one of the nodes? If there is, you found a counterexample. Because you can translate back into the P's and Q's, but eventually you're talking about cycles in this graph. If there is not a cycle in this graph, which can be a quick search, M satisfies phi. So I hope you now appreciate the genius of what a model checker does. It has avoided all searches. It's looking at just transition systems and eventually looking for loops within transition systems. Questions? Is it clear why this would work? I see some puzzled faces, so give me some question, even if the question is, what is this?
Sorry, could you just repeat one more time? So if there is a cycle.
Yes. So what is a cycle in a Büchi automaton? It is if there is a cycle which visits an accepting state, then that's a accepted path, right? We just saw examples of that. Now I'm looking at the product of my transition system and my Büchi automaton, and I claim the same thing. If you visit any of these accepting states in some loop, right? There is no loop here. You go to this, but you never come out. This transition is the opposite way. So if there is a cycle in my product which visits an accepting state, that means there could be an eventual trace or a path that visits that state infinitely often. Because what is infinity in a graph? It's a loop. Okay? And we are exploiting that property. If there's a loop, then let's look at whether there is an accepting state in that loop. And if there is, we found a counterexample. You are done. Model doesn't satisfy phi. You can go to your designer, say, here is the trace which doesn't satisfy phi. If there is no loop, or if there is a loop without any accepting state, you are done again. You say for every trace, it satisfies phi. Because there is no accepting path in B of not phi, which is what is the basis of this product. Okay? So we can complete this picture by saying we can take the product of both and then we just look at the counterexample or a loop. And so literally the last thing is that you can find this loop using depth first search, which is a very efficient algorithm. So all you have done, or the model checker has done, is built this product. And so here's an idea. It has built this product. It will start from any state or the initial state. It will start looking at nodes and trying to find whether there's a cycle. So it keeps track of where it has previously visited as it is traversing this graph. And so here it found an accepting state. And then it sees, is it possible for me to reach any of the nodes I've visited before from this accepting state? And if that is the case, you have found this cycle. So you have found a cycle or an accepting path which is valid in B of not phi. Therefore, your model doesn't satisfy phi. And if there is no such cycle, your model satisfies phi. You don't have to program this yourself, but like always, when we spend all this time on parameter estimation and algorithms, I don't just want you to become users of a tool. I want you to understand what it is that the tool is doing. And this is exactly what it is doing. Okay, so this is a good point to stop, but if you have any questions, now is a great time. But we are pretty much, this is what model checking is. The whole trick is LTL to Büchi and using a product automaton, and then it becomes tractable. Okay, so I find it very, very interesting how this works. Hopefully, I could share that enthusiasm with you, but we are done with model checking. So we'll, in the next week, jump out back into the hot model. Okay, so now is a good time to stop.